try. This is going to be the executive summary of the QFT, or basically QFT under 10 minutes and 10-15 minutes, I hope, and without basically any maths or no mathematical explanation of what's going on with the gates. So to understand the QFT in an intuitive way, you have to understand what inputs and outputs is designed for. This is really important, and you've got typically two different ways to see it, right? So you've got this way of seeing it, where you start like this version of the KFT is designed to take in as an input um, a frequency, right? Like, so you could think of this as frequency number 1, right? You could also have in here multiple frequencies, right? For example, here's a combination of frequency 1 and frequency 3, and the output of the algorithm you see here is basically a phase encoded it's sort of phase encoded signal data. So let's imagine that we just say 1 because it's easy to see, right? So this is telling you on the output side is that you're gonna have, if you take a look at the angle of the phase, how is it moving forward across your different states, it's actually doing a full cycle, right? So it's using all your, like, starting from 0, 0, 0 as the first point where you hold data until the very one, the last one. If you'd have another one, then you would kind of basically go back to a phase 0, so to say. So that's the idea, right? Phase 1, frequency 1. So if you go back to 0 and say now I want to encode 2 as an example, you see that it's going to give 2 cycles, right? So that's the way this circuit is designed. You've got also this other version, which is basically sort of the inverse of that, right? And here, just to make it clear, this is the input preparation, and if I go up and here the input preparation is basically here. So I'm just using the QFT, built-in QFT gate to prepare basically that box is that entire circuit. So what I'm just doing here is I'm just using that to prepare, just so you see, to prepare a valid input state, something that it's easy to then kind of shoot at the algorithm, and then you can see an outcome that makes an output that makes sense. So you've got here basically a 1, right? It's the same that I show you on the other circuit. And so what this circuit is designed for is designed to actually tell you which frequencies these signal data is encoded from, kind of, right? So if you've got a 1, it matches 1. If you've got a superposition, as I said, for example, just to show you the display here, so if all we do is something like this, so we get like 1 and 3, basically that's your input data, and then at the end you get 1 and 3. That's, yeah, so again, and you get it into a superposition, right? So you would actually have to basically do several runs so you can actually get those numbers, but that's the idea. Okay, so once this is clear, let's go ahead and try to unpack these two circuits, because they're really similar. And actually, if you it's one curious fact about this algorithm is if you basically concatenate 3 times the QFT, it's kind of circular, because as you can see in the circuit, we are basically doing rotations. It's all the time rotations. So what's really happening here is that you're basically, the way you encode that, right, is that you want each qubit that makes your number in binary to have a particular influence on how this is being rotated. So technically, you've got those Hadamards here that build you the basis superposition, and then you've got the controlled rotations that do those shifting here. So just to show you, the easiest way to see that here would be to show you what's happening at that point in time here. So we'll go back to the example of 1, right? If I show you what's the state looking like here, right? So in this case, basically, all what we want to do here with the 1 is we want to have a superposition that's that, right? So that ends up in this state. So if you pay attention, there's some sort of cycles in here that repeat, of course. So this portion of our output is basically the opposite, it's sort of like a mirrored version of this one, because yeah, you're trying to give a full cycle, so you're gonna have those two steps, right? Those two halves. So this is something that you're gonna have with the Hadamard, right? So the Hadamard itself is a gate that's gonna already, it's gonna basically expand the to the rest of of your possible states, and it's also gonna rotate because you have the one in here, right? So that's already what the Hadamard does with the one is it creates that superposition, right? The minus state, which already has that phase in here. That is what we really want to have. So, and that goes, all the way here, and that's cool, so to say. But what's interesting to see is basically how is this set of rotations affecting the whole thing. So, and maybe it's going to be easier if I decompose them. So, if we do this, because at the end of the day, that's just a compressed way of saying, that's what we're doing. So it's gonna be easier because we will then see step by step. Um, so the cool. So what's happening here, as you can see, so what's happening is that this first rotation is telling you, okay, so from our states in here, all the states that have a 1 1, so all the ones in here, rotate them like by 90 degrees, right? And when you exactly, so and when you basically move forward to the next one, what's actually happening here is you're you're basically now saying the ones that have the 101 pattern. So this is this here. Rotate them by 45 degrees, right? And so, but pay attention that in those two cases, it's kind of accumulated, right? And then you end up with the latest one being exactly this, where you're now saying the ones for the pattern 1001, because that's what those control Z gates are doing, right? Like if you take a look at the system level, that's one of the ways to interpret the control Z. It's then for this part here. Exactly, for this part here is, oh wait a second, I think it's going to be easier if I show you this in another way. Give me a second. It's going to be way easier if I decompose this differently. Yeah. I hope I'll be able to stick with the timing and the 10 minutes, so that's definitely going to be easier. Is it? I think it's gonna be easier, yes. So basically, because now you can see, it's easier to see if you start basically at the lowest value qubit. So this is everywhere we've got like a 1 in this qubit in here, we're rotating. Wait a second, that's wrong. Exactly. Here we go. So those were minus. So basically you can see here that it's rotating those elements by 22.5 degrees. And so what we're doing step by step is we're taking, because the next qubit has more weight in the full representation of that binary number. You're basically then taking that and also and kind of like adding here, right? And here you're adding those 45 degrees. So in the cases you already rotated before, because there's a 1 as well, that basically sums up, and so you've got 67.5 degrees, and so you're kind of creating that slope step by step, and then when you're in the variable for the next level, then you're actually adding you know, this extra 90 degrees, and so you're kind of all the bottom part here. Um, so that becomes goes from 22 to 112, right? And these 235 and these two like 157. So your each qubit kind of gives you that extra weight in there. Because at the end of the day, that's a binary number. And then the last kind of, you know, the cherry on top of the cake is basically the Hadamard, which basically doubles you, or you know, fills up the rest of the superposition, um, and it adds like 180 degrees shift to that part here. So everything goes 180 degrees, and this is because we've got a one in here, right? So that's the essence of this version of the circuit. Basically, rotating as a function, or rotating the phase as a function of the importance and the weight that a particular qubit might have in the actual decimal representation, binary representation of your frequency, and the same, and that extends linearly to superpositions, right? I mean, there's nothing here that changes. The reasoning is the same if you've got something like that. Um, this qubit in here is going to be both 0 and 1. So you're kind of gonna have those two different situations being developed within your superposition. So this is basically that version of it. This part of the QFT is maybe a bit less intuitive, and I really recommend that you take a look at the in-depth series of the QFT so you can see what I went through trying to understand that. But the idea here is that you're kind of doing the opposite. Instead of starting from scratch and setting up, like encoding the data in your superposition, what you want to do here is you want to figure out where, how does this, like, you know, how do we come here to that data encoding pattern, right? And the way you want to do that is you want to do that by, in a similar way, you want to identify, okay, what was the value of the qubit that led to this particular set of rotations. And one way to do this is you're basically trying to identify cycles, because we said here that basically what you're doing at the end is if you have a 1 in here, you're actually going to have a full cycle. So this means that the two halves have to be mirrored, right? So this is an indication that there is going to be a 1 in here, and so that's useful for this case, because if the first thing that we do is we start doing a Hadamard here, right? That's what the Hadamard is going to do for us. So the Hadamard is going to basically detect exactly that pattern. So it's going to see, okay, here I've got basically a mirrored pattern. So I'm gonna get rid of that and pack it all into the portion of my different amplitudes that have a 1 for that qubit, because that's how the Hadamard compresses things. And so basically what this is telling you, right, is already that you know that the qubit up here is going to be a 1, because this pattern indicates you that it's an odd number, like what you have in here. If this cycle would be basically the same, so it would be just a repetition, for example in the case of 2, right? So you're basically now have 2 cycles, so this means that these and these, they are not mirrored anymore, they are the same, because you're doing two cycles. Now the Hadamard is gonna basically do the opposite. It's gonna get rid of these, right, and then pack it all into the half that starts with a 0. So what the qubit value here is telling you is that, well, that this number that we're looking, right, that we don't know about, because this is in theory something you don't know, it's gonna have to be an even number, right? Because only even numbers will kind of generate that kind of pattern in the input. And so basically what this is telling you is that essentially you can summarize it like the value of this qubit is literally telling you the actual value of what you should have as the lowest qubit in your final result, right? And so that, and then you can extend that idea to explain the rest of the algorithm. So um, the let me delete that. So exactly. So basically, what you then do from here is you apply the inverse rotations that what we've seen here, because that's what you're assuming is that um, if this is a one, right? Um, if this is a one, we basically have to uh, kind of correct for the the weight rotations that you experience on this side, right? That you're rotating as a function of the values in here. So you want to go back. It's sort of you want to go back to one step, right? And so you can apply a Hadamard and then identify the next pattern. That's probably, maybe it sounds too less intuitive, but if you go through this and you think about that part of the algorithm as the inverse of this, it kind of makes more sense. But intuitively, you're basically rotating counterclockwise based on the weight of each of the qubits, so you get there. And then basically, um, as you get down here, that's what you. So you're basically, each qubit you're recovering, it's the value that the qubit. This one was the value that this qubit is going to have. This one is here is the one that this qubit is going to have. That's why you have the swabs in here at the end of the day. It's just that might seem a bit confusing because they are at the very end of the circuit, but this is what you're gonna. This is what you're doing basically. You're identifying the cycles, and that type of that outcome after each Hadamard is telling you what is the value of the qubit that you should have, but not the same qubit where you apply the Hadamard, but the one that's kind of opposite into your register. Yeah. So that's basically QFT. It's nothing more than that. Yeah, nothing more than that. The key points. I think this circuit is easy to understand. You might have sometimes a different arrangement of the controlled rotations, but at the end of the day, it all sums up to the same thing. This is a bit tricky to understand, especially because your input is superposition, so that might be a bit less. It's a bit more complicated to understand intuitively, I would say, for someone who's approaching this from scratch. The two key points to understand is, why do we have swaps in here, and what are those rotations doing, and why they are backwards, why they are like minus one, right? So why are they the inverse of the other rotations? And the explanation is, again, simple, right? Once you're already compressed half of the cycle, then what you're trying to do at the end of the day is you're trying to back engineer, like reverse engineer what, maybe not, it's the wrong word, but you're trying to basically find what are the values of the qubits that could lead to that type of cycle. And so that basically implies that each of these qubits, as we said in the beginning of the video, has a proportional impact on the rotation. So you're undoing that. You're literally undoing that. You're kind of applying an inverse rotation based on the actual value, or based on the actual position and weight that a qubit would particularly have. And remember that you're operating across the entire superposition. So if I manage to move this, I'll make it clear, and I'll probably leave it. I think we'll be under 20 minutes. So if now I show you what those things look like, that's basically. So you see that here nothing has happened. Yeah. Okay. Yeah, basically nothing happens here. Yeah, because basically there's no. That's the gist of it, is that nothing happens here, because basically we've got we've basically got a 0 here, right? So that's telling you, and I know because we put a 0 here, but so the fact that nothing is happening is because there's no influence of that particular qubit, and that means that it's a 0. So that's why nothing is happening. So the Hadamard is able to pick up already the pattern, right? So this is sorry, the other way around. It's telling you that the influence is here, so that's number 1. So, and that's why you've got like the inverse pattern here. Anyway, it's a bit tricky to talk about those things in a clean way. So, yeah, this is basically it. This is basically the bunch of rotations, and just making sure the swaps here make sense, because the cycle is telling you about the value of the opposite qubit. Opposite as in opposite within your qubit, with your bitwise or qubit-wise representation of the frequencies, and that extends linearly to superpositions as well. You're gonna have, you're basically gonna have like if here you've got like if here after the Hadamard you don't have a clean you don't have that cleanup here where it's empty, it means that it's not just 0 1, it means that it's a combination of both. So it means that you kind of then go ahead and do the calculation for both possibilities. That's what the circuit is doing within your superposition, and then you're going to end up with with more than one amplitude in here. So that's the point. Cool. I hope that it was clear. I hope that it was not confusing. It's a bit of a long executive summary, but I think that pretty much summarizes everything that I've learned about the QFT in the past days and weeks.